Question 23 of this paper reads, a sound wave has a frequency of 2,500 hertz and a speed of 1,500 meters per second. What is the shortest distance from a point of maximum pressure in the wave to a point of minimum pressure? So in order to answer this question, we both have to have a conceptual understanding of a sound wave as well as sort of a theoretical understanding of mathematics. It's really about wavelength. This question is about the wavelength. And so for a longitudinal wave, you've got some parts of air where all the air particles are really sort of crunched up together. They're compressed. And then there are places where the air is kind of spread out a little bit, okay? And then there's places again where they're crunched up, okay? So longitudinal waves like sound waves are characterized by regions which are compressed and regions which are rarefracted, okay? Rarefraction is like the opposite of compression, spreading out. Wavelength, the wavelength of a longitudinal wave is the distance from like the middle of this compression to the middle of this compression, from compression to compression, or from rarefraction to rarefraction. They're asking about the distance between a point of maximum pressure, which would be kind of like this point right here, to a point of minimum pressure, which would be like this point right here. If you can read through this and go, oh, they're asking me for 1/2 the wavelength, then you've really sized up this question very well. You can read through this and go, oh, this question is about a wavelength of a sound wave, but it really wants me to calculate half the wavelength because the distance from maximum pressure to maximum pressure would be the wavelength. So the distance from maximum pressure to minimum pressure would be half the wavelength. And so this is very helpful to kind of go, oh, I need to calculate the wavelength and take half of it. How do we calculate the wavelength? You can't determine the wavelength on an oscilloscope unless you know the speed of the wave. They conveniently give us the speed up here. The oscilloscope can give us the period, and we know from the period we can get the frequency, but we can't deduce the wavelength by just like reading off how long it is on this display. In other words, this wavelength is not 1, 2, 3, 4 centimeters. The display shows it as 4 centimeters, but to really deduce the wavelength of this wave, the wave whose sort of data is represented on this instrument, we have to know the velocity of the wave. And we need to know the equation, velocity of a wave is equal to wavelength times frequency. They might expect you to know that, for example, the velocity of light is the speed of light, and so they wouldn't be friendly enough to give you that, but they'll have to tell you, if it's like a sound wave. And so here it's not sound in air, that's much too fast. This might be like sound in water or something like that, more dense. So we can solve for the wavelength by taking the ratio of velocity to frequency. Wavelength is the ratio of velocity to frequency. It's a nice little lyric there from a hit song that swept the nation last spring. Well, not really, maybe 1,500 meters per second divided by the frequency up there, 2,500. 1,500 divided by 2,500 is the same thing as 15 divided by 25. Is the same thing as 3 divided by 5. Same thing, 6 times 6 times 0.6. Okay, is the wavelength. No calculator needed if you can juggle that in your mind. So if the wavelength is 0.6, many students will be so satisfied with that calculation that they'll incorrectly choose choice C. But again, if you sort of size up the question like this initially and go, oh, as soon as I get the wavelength, I know to take half of it. This is asking about what is half the wavelength, then you'll correctly choose choice B, right? Half of 0.6 is 0.6. Any questions on that one? Again, the conceptual understanding of like this part of it, just knowing, oh, they're asking me for half the wavelength, that's the hard thing I think about this question. You should be familiar enough with like this math that you could substitute in a speed and a frequency and get a wavelength or whatever. Okay, that's not too bad there. Come easy go. Now on to the cathode ray oscilloscope question. It says we got a sound wave here and it's displayed. They give us the time-based setting, so let's write what we're given. 2.5 milliseconds per centimeter. Okay, each one of these is a centimeter. I want to know how many centimeters per wave. So there's a quarter of a wave, there's half a wave, there's 3/4, there's a full wave occupying exactly 4 of these centimeters. So it is, I want to cancel out centimeters. So I'm going to kind of use the units to help guide my calculation. 4 centimeters per wave. When I multiply these two, I don't have centimeters of display space. milliseconds per wave. Nice, that's a period. That's something, you know, useful about the wave. The time period of the wave is the amount of time it takes a single wave to propagate. So 2.5 times 4, what's that? 10? 10 milliseconds is the period, and then the frequency, you may recall, is 1 over the period. And so 1 divided by 10, and now I'll convert to milli. Okay, you could have done it up here. Convert to milliseconds whenever you want. So 1 divided by 10, 1 divided by 10 by 10, 100. 100 hertz for that one. Okay. Sometimes you will have to calculate the time-based setting. Like they'll tell you what the frequency is and they'll say, so what must be the time-based setting of this? And as long as you kind of keep track of the units, all the calculations are pretty much the same. So we'll probably see an example like that before the end of the day. We will find one like that. All right. There's another one down here that I wanted to do, at least one more, maybe the next one too, just to kind of preview tomorrow. This one is a Doppler effect one. Okay, it says a car traveling in a straight line at a speed of 30 meters per second passes near a stationary observer while sounding its horn. The true frequency of sound from the horn is 400 hertz. The speed of sound in air is 336 meters per second. What is the change in the frequency of the sound heard by the observer as the car passes? I think this is a tricky question because the observer is going to both hear a sound that's higher pitched than 400 as the car approaches. You're going to hear a sound like 400 and something, right? Bigger than 400, high pitched. And then as the car passes by, it becomes low pitched. Right? The Doppler effect is and you just kind of remind yourself of that. So the change, it really requires 3 calculations, I think. We have to use the Doppler effect equation to calculate what is the frequency on approach. We have to use it again to calculate what is the speed, you know, as it recedes away. And then we have to take the difference between those frequencies, right? Because that will be the change in the frequency heard. Right? In other words, what's the difference between the meow, okay, if all of those are around 400, but what's the total change in that? That's the question. All right, so let's go through all of those there calculations. So I'm going to calculate the observed frequency twice, okay, like the observed frequency upon approach and then upon separation. So it's going to be the frequency of the source, 400, times the speed of sound, which is 336, divided by the speed of sound again. And to make this number bigger than 400, I need to subtract down here. So I'm going to subtract away the 30 meters per second. That's the velocity of the source, right? The car is traveling at this speed. So the source of the horn sound is this fast. That's the speed that the wave can propagate in air. And that's the original frequency, the frequency of the source. And so we can solve for the observed frequency this way. 400 times 336 is a big number. When I divide that by 306, though, it gives me the observed frequency, higher pitched, 439.2 hertz. Okay. Students that are like, oh, I did this calculation correct. The difference in the frequency is the difference between 400 and 439. This person observes a change in frequency of 39. They didn't really read the question carefully. It passes near a stationary observer. Okay. It passes them. So they hear both the higher pitch noise right as the car passes, right? Then they hear the 400, and then as the car speeds away, now the car is still creating a sound wave, speeding away from the waves that it just created. And so it's going to appear to us that those waves get stretched out, longer wavelength, which means they're less frequently occurring. So it's going to be a lower frequency than 400 when we do the calculation again. So this time we're going to calculate 400 times 336, it's still the same, you know, frequency of the source times the speed of the wave divided by the speed of the wave, but this time we're going to add the 30 meters per second of velocity, right? So we're going to decrease this frequency now. So now I've got 400 times 336 to give me that big number again, 134,400 divided by this time 366. And that solves for an observed frequency of 367 hertz. And so that's a lower pitch than the 400, you know, hertz that the horn actually makes. And so this is the meow. And the difference between E and meow is .72 hertz. Note that you really do have to do both calculations and take the difference. You can't say, what's 39 doubled? Like, oh, if it's that much of a difference upon approach, then it's going to be the same. You know, if you just double 39, you'll incorrectly get this answer. So that is an answer that's up there. There's no shortcut there. You can't just say, oh, I can just calculate this and then it's going to be the same change on the other side of it. That's not the way the math works here, right? You actually calculate the change in frequency observed at 72 hertz. It's not just double the change that you hear upon approach. All right. So calculations like this, you got to set it up, you know, twice, solve it, take the difference. That takes a couple of minutes, right? So there should be other ones that are conceptual, like, hey, which list shows electromagnetic waves in order of increasing frequency? So increasing frequency means decreasing wavelength. Okay, well, I know gamma rays have the shortest wavelength, and so I want one of these answers probably. And right away I can eliminate that one because radio waves are the longest waves, so they would go over here, so it's got to be choice B. So see how that one took literally 5 seconds, you know, if you understand the physics. Longest wave, and then infrared, and ultraviolet, and gamma. This is increasing frequency, increasing energy, decreasing wavelength. Okay, and we'll study this in its own right tomorrow. That really is one that's like requires a bit of memorization. Okay.